me introduce basic pigeonhole principle and how to employ that in proving this claim. Here is the principle. Given n pigeonholes and at least n plus 1 pigeons. So now the principle says the following. In any distribution of n plus 1 pigeons into n pigeonholes, there exists a pigeonhole containing at least 2 pigeons. For example, let's assume you are given say 3 pigeonholes and say 4 pigeons. It says in any distribution you can come up with any distribution of 4 pigeons into 3 pigeonholes. Now let me assume this is 1, 2, 3. You are trying to distribute 4 pigeons. Let me place pigeon 1, A1, A2, A3. Now where do you place A4? If you place A4 here, then here is a pigeonhole containing at least 2 pigeons. If you place it here, here is a distribution where here is a pigeonhole containing 2 pigeons. You can even come up with a distribution where all of them are placed in one pigeonhole. So that's precisely what our claim says. Here is a pigeonhole containing at least 2 pigeons. Now, identification of pigeonhole, pigeons, and the distribution part, that is where the challenge lies for a specific case study. For example, case study like this, we have to identify what exactly in this represent pigeonholes and pigeons. Once that is done, and once we establish this gap that there are n pigeonholes and at least n plus 1 pigeons, simply employ the principle and we are done. Fine. It says in any distribution, and you can come up with any distribution, you see that at least one pigeonhole containing at least 2 pigeons. I am only saying at least one pigeonhole, meaning you can even come up with a distribution. So you see that P1, P2, P3. I may place A1, A2 here and A3, A4 here. Now you see that at least one pigeonhole containing at least 2 pigeons. You may find more than one pigeonhole containing this as well. Okay. Now, for this case study, what are pigeons? What are pigeonholes? Which we shall see next. So let's bring in PHP. So case 1, there exists W such that degree of W is n minus 1. And we observe that if this is the case, then for all W, we know that there does not exist a W whose degree is 0. Then for all W, its degree is between 1 and n minus 1. There does not exist W such that degree of W is 0. this case, what are PGNs? What are pigeonholes? So PGNs are vertices, then the pigeonholes, they represent degrees. So possible degrees are 1, 2, so on up to n minus 1. Now what are PGNs? PGNs are vertices, so they represent V1, V2, so on up to Vn. What do you do? If degree of say Vi is L, then place Vi at the pigeonhole labeled L. So where do you place Vi? If degree of Vi is 2, you place Vi here. So you come up with a distribution in such a way that suppose there are 3 of them, and degree of say V1 is say 1, and degree of V2 is 3, and degree of V3 is also 3, and so on. There are n PGNs and n minus 1 pigeonholes. Then say degree of V4 is say 2. Okay. Now you see that if degree of V1 is 1, you place V1 inside this. Degree of V2 is 3, then you place V2 here and V3 also here. Degree of V4 is 2, so you place it here. Okay. So it's 1 to n minus 1, so which means n is 4. You see that 4 of them, and there are 4 vertices trying to take a value in the range 1 to 3. And you naturally see that there will be a pigeonhole, or there is a pigeonhole, and whose label is say L. In that you find at least 2 PGNs. And what are PGNs? PGNs represent vertices, which means these 2 vertices are the desired vertices, 2 vertices of equal degree. These 2 vertices correspond to 2 persons in the underlying application. So these 2 persons represent the desired client, meaning they both have equal number of friends. Okay. I repeat, case 1, there exists W such that degree of W is n minus 1. Then for all W, degree is between 1 and n minus 1. And if that being the case, here is a distribution. Pigeonholes represent degrees, which means the labels are 1, 2, so on up to n minus 1, as the range is from 1 to n minus 1. What are PGNs? PGNs are basically vertices. If degree of Vi is L, then you place Vi where onto the hole which is labeled L. For example, if the pigeonholes represent 1, 2, 3, and PGNs are V1, V2, V3, V4, suppose for this example, you see that V2 and V3 are placed in this, which means these 2 vertices have equal degree, or these 2 persons have equal number of friends. So in general, n PGNs into n minus 1 pigeonholes by PHP. PHP says n plus 1 PGNs, n pigeonholes. So they differ by at least one, right? Now here it is n PGNs and n minus 1 PGN holes. By PHP, there exists a PGN hole containing at least 2 PGNs. So equivalently, there exists a PGN hole containing at least 2 vertices or 2 persons. So now they represent the desired set. So that is precisely what we want. So those 2 vertices are the desired vertices of equal degree. So we have completed our analysis or the proof for this case. So for other 2 cases, we establish a similar PHP argument, which we shall see next. For case 2, we see that there exists W such that degree of W is 0. Then we know that there does not exist U such that degree of U is n minus 1. That shows that for all V, degree of V is such that it is between 0 to n minus 2. Correct? Now, n PGNs and the values that these PGNs can take, now they represent vertices. The values that this can take is from 0 to n minus 2. Correct? So the values that these vertices can take, namely degrees, is from 0 to n minus 2. So there is a PGN hole whose labeled as 0, PGN hole whose labeled as 1, so on up to n minus 2. For example, 0, 1 and 2. Suppose degree of V1 is say 0, degree of V2 is 1, and say V3 is 1 and V4 is 2. Then you place V1 over here, you place V2 and V3 over here, and V4 over here. Then these 2 vertices are the desired vertices whose degrees are same, or these 2 persons have equal number of friends. So you see that how many PGNs? 0 to n minus 2 PGN holes, which means there are n minus 1 PGN holes and n PGNs. So by PHP, there exists a PGN hole containing there exists a PGN hole containing at least 2 PGNs, which means there exists a PGN hole containing at least 2 vertices or at least 2 persons, and that PGN hole in particular, the label of that PGN hole will tell you the value of that number, the number of friends. We say equal number of friends. How many friends they both have will be represented by the label of that PGN hole. Fine. So on the similar line, let's look at case 3. Case 3 says for all w, degree of w is between 1 and n minus 2. If it is 0, it is taken care here. If you find a vertex of degree n minus 1, it is taken care in case 1, which means when you come across this case, then the range of degree is from 1 to n minus 2. Now the range is 1, 2, so on up to n minus 2. Now 1 to n minus 2 is n minus 2 PGN ores, and you have n PGNs. You distribute n PGNs or n vertices into n minus 2 PGN holes. So when you distribute n minus 2 n PGNs into n minus 2 PGN holes by PHP, we see that there exist two vertices of equal degree. So if degree of V2 is 2, you place it here. If degree of V7 is 2, you place it here. Now the possible degrees are 1 to n minus 2, and there are n vertices. So in fact, the number of PGN holes is 2 less than, at least 2 less than the number of PGNs. So you see that in any distribution, we will find 2 vertices mapping to some PGN hole. The label of that PGN hole will tell you the value of the degree, meaning we say equal number of friends, the value of that number is given by the label. So now what we have seen through this technique is the following. Principle is so simple and elegant, the way it is applied is quite powerful. So the claim comes from graph theoretic domain, but the way it is proved is using a principle. It is it's quite different from the way we see things in graphs. It talks about something called PGNs and PGN holes, but if we carefully model graph theoretic problem by identifying PGNs and PGN holes, and this principle plays a vital role in proving many claims in graph theory. So you can also say PGNs as say balls, PGN holes are boxes, and there are other variants of this which you come across in literature, but irrespective of that, the principle is remain the same, and application is powerful. For example, identifying that the labels of PGNs, they come from this range and they come from this range, that's where challenge lies. Often that is not explicit in the question. The question will not even talk about PGNs and PGN holes. So somewhere the research lies in identifying PGNs and PGN holes. Most importantly, that the number of PGNs is at least one more than number of PGN holes. Okay, so in this case if you see, and it is 2 more, and in this case if you see, it is 1 more. So you have to come up with the distribution, or you have to come up with PGNs, PGN holes in such a way that number of PGNs is at least 1 more than the number of PGN holes. Then you can straight away bring in PGN hole principle and complete the argument. There are many interesting case studies of this type. We shall explore more in subsequent lectures.